So welcome everyone to the Senior Researchers Panel. You can see on your screen some very distinguished quantum information science researchers. It's a great honor to have all of you here today. I'm going to ask each of you a question to start out and introduce you after. So the question is a little bit of a fun one. What was the field like when you were a young quantum information scientist? Maybe what's different now, what's the same? What has changed. So we'll start with Ivan. Dr. Ivan Deutsch is a Regents Professor of Physics at the University of New Mexico, where he is also the director of the Center for Quantum Information and Control. His research expertise is in quantum information, AMO physics, and quantum optics. He has too many awards for me to possibly list, but I will say, having a few friends at UNM, I can say that he's known for his wonderfully pedagogical lectures, albeit some notoriously tough quantum optics homeworks. So welcome, Ivan. What's different about the field since you were a young quantum information scientist?
Thank you, Ryan. That's best introduction ever. I appreciate it. Yeah, it's just interesting. So, I'll date myself. I got my PhD in 1992. And at that time, there was no such thing as quantum information science. What there was, and why I got into the field, was people interested in the foundations of quantum mechanics. And when I started my PhD was around the time that Alan Spade did his famous experiment on Bell's inequalities. And I was really interested in understanding quantum mechanics itself. And those of us who were interested in that, a lot of us went into quantum optics because that was the arena in which tests of quantum mechanics were done. And I think it was an interesting time as it transitioned, as we learned to understand that these foundational questions about non-locality and decoherence actually had implications for what we can do in information processing. That was, was an exciting transition that happened around the time I was a postdoc. Shor's algorithm came out, and it was a revolution. And so I think one of the lessons I take away from that is that you just never know what fundamental research is going to do. Who knew that tests of Bell's inequalities would have technological implications, or that studying decoherence, as Serge Roche did, would become a quantum error correcting code for cat qubits. I mean, you just never know. So basic science is truly important for the advancing of, technology as well as knowledge.
Awesome. Thank you, Ivan. Our next panelist is Dr. Eleanor Riordan. Eleanor is a senior research scientist and the lead of the Quantum Artificial and Intelligence Lab at the NASA Ames Research Center. She has a background in mathematics, having done a PhD at UCLA and postdoc at USC. And afterwards, she worked at FX Palo Alto Lab on a lot of topics, including quantum computing, also cryptography, image reconstruction, and more. If you're looking for a gentle introduction to quantum computing, then look no further. Eleanor has published a textbook exactly with this title, which I would all recommend and encourage you to read. So
can't quite see here, but there it is.
Thank you, Eleanor, for joining, and I will pass the same question to you. What's new and what's changed about the field since you were a young quantum information scientist?
Thanks, Ryan. I started looking at quantum computing in 1996, 1997, and got super excited about it by reading the introduction to Steen's tutorial on quantum computing. It was a fascinating blend of physics, information science, computer science, mathematics. And then he had literally 3/4 of a page of quantum mechanics. And I was completely lost. So Wolf Pollock and I, who's the co-author of the book Ryan mentioned and Steve showed really sort of back engineered that tutorial, which was written for physicists so that it would be understandable to mathematicians like me, computer scientists like Wolf, and engineers. And really, I felt like I was in the right place at the right time. And just enormously lucky to be able to join this fascinating field just as it was taking off. Though it was so far in the future that at my job, they were sort of willing to let me do it on the side, but it wasn't going to be the focus of work there since it wouldn't affect the parent company's bottom line within a reasonable amount of time. I would say that the biggest change, and I hope this will make you all laugh, is that when I started in the field, it was fantastic. I looked at it, and unlike mathematics, where it was hopeless to know all the major results, I'm like, wow, this is a field where you could really understand all of the major stuff that's going on. And that was maybe a little bit unrealistic even at the time, but there was really a fair amount of truth in that. And that's just no longer possible. And I don't think I could have imagined that there would be so many students giving talks on quantum computing at an event like this. Back when the number of students at this event, I believe, is more than there were people working in the field when I started looking at it. So the field is just really grown in many, many ways. And the other thing that really has been amazing is to see how fast the hardware has advanced. I wasn't sure when I started looking at this that I would see quantum processors that were competitive with anything, let alone with the largest supercomputers in the world. So it's just amazing to be alive and see that and able to work on it.
Growth of the field has really been great. We have around 1,000 or so registered participants for this event. So awesome, thank you for that. And our last panelist is Dr. Stephen Girvin. Dr. Girvin is a Eugene Higgins Professor of Physics at Yale University, and he is also the director of the Co-Design Center for Quantum Advantage at Brookhaven National Lab. This is one of the 5 DOE National Quantum Information Science Research Centers in the US. Together with his colleagues, Michelle Deveray and Rob Shulkoff, Professor Girvin developed the circuit QED architecture that has become the industrial standard for quantum processors based on superconducting qubits. So it's a great honor to have you here, Steve, and I will pass the same question to you. What's the same, what's changed since you've been a young quantum information scientist?
Well, for me, the premise of your question is wrong because I never was a young quantum information scientist. I was old when I became a quantum information scientist, but I started out, I got my PhD in 1977. I started out life, I wanted to be an experimentalist when I went to graduate school, but I somehow accidentally became a condensed matter theorist. And I thought about, correlated electrons and the fractional quantum Hall effect and a little bit about superconductors. And I didn't even know later that there were crazy people beginning to think about the idea of building quantum computers, or I just had never heard of the field, knew nothing about it. And in 1998, somebody, I don't remember who, showed me Yasunobu Nakamura's article in which he saw the first time domain evidence of what's effectively Rabi flopping in what is now a superconducting qubit. And I was like completely amazed and stunned. And then I discovered, oh, there's a whole effort of people thinking about using these kinds of quantum devices for information processing. I had no idea. And that was like a amazing moment in my career where I'd been doing condensed matter theory for a long time, and I decided it was time to switch fields and do this completely new thing. And then by happy chance, a couple years later, I was giving a colloquium at Yale, and I met my now colleague Rob Sholkoff, and he was building, Cooper pair boxes and measuring them, and we had this amazing conversation about how you might connect these Cooper pair boxes to microwave photons in cavities. And I just had a phase transition in what I worked on, and I had to stop and learn quantum optics, which, that took several years after I moved to Yale. And the first thing I learned was that people in quantum optics know a lot more quantum mechanics than condensed matter theorists. I mean, we knew nothing about dynamics. We knew nothing about coherence. So it was eye-opening to learn about quantum trajectories and, just all these techniques that have been developed in quantum optics. And one of the great things now is, this goal of building machines that are truly quantum for sensing and for information processing. You can now have conversations with people from other fields. Condensed matter physicists are getting invited to the atomic physics meetings and vice versa. And it's just been so great for the field. The atomic physicists were starting to do Bose-Einstein condensation and stuff, and they had to learn things like entropy and temperature, which were complete news to them, and we had to learn stuff like coherence. So it's really been so refreshing for me personally, and for the field generally, I think, to blur the lines between these different disciplines. And as Eleanor said, things have subsequently really accelerated, and it's just stunning to watch the progress. So it's just an amazing time, and we're relying on you young people to keep this moving forward.
Excellent. Thank you, Steve. Feeding off this subject, we do have a lot of people, a lot of young researchers at this conference who are perhaps coming in from other fields and may not be experts in quantum information yet. Maybe they're just getting started, or maybe this is all completely new for them. Going off of this, do any of you have advice for such a demographic? How do you get into the field? Is it necessary to pursue a PhD now? Or can you do other things, maybe online courses? Companies like IBM and others have this now. What are your thoughts around this? Maybe starting with Eleanor?
Sure. So I often get asked what people should learn as undergraduates, and the pat answer is everything. It's amazing how almost anything, even things you think will be irrelevant, end up being useful. I think Steve's comments suggested some of that, as people from different fields were surprised what they had to learn. But I'd particularly emphasize both linear algebra and probability theory. In terms of a PhD, I think people often look at it the wrong way around, and they think that this is something you need to do to get to do your real work. And the way to look at your PhD is that, as tough as it is, this is just a wonderful opportunity for you to work on something that you want to work on with relatively few distractions compared to what your life will be like later. And so really take the opportunity to enjoy the PhD with all its pain. But it really is a time for you to find something that you really want to work on, and and can put most of your effort into that. And of course, there are other ways of joining the field to some extent. And it may make a lot of sense for you to join a group, work for a few years, and then go back and get a PhD. But I'm for anyone who seriously wants to do research, it's just a wonderful opportunity to have that time to work on those things.
I think that's really great advice. Steve, do you have anything that you might want to add to that answer?
Well, yeah, this is a question that's being asked, at the national and international levels. There are young people who are just starting, what should they study? There are people who are already practicing engineers who have various expertise in software or microwaves or control circuits. And how do they how do they make we need them to build these marvelous machines. Physicists don't know how to do all these things. And but they can't take another 7 years and get another get a PhD in quantum physics before they can start being productive. That's not going to work. So it's a very there's a lot of interest right now in how do we cross-train people, give them enough knowledge that they can start picking up the rest by osmosis, essentially. And several of us are involved in a Ceph workshop that's producing a sort of white paper that's going to be published in IEEE on, how do you start programs to teach people about quantum information science with different backgrounds and different levels of preparation. And so there's a lot of people thinking about this question. But, I came from condensed matter theory. My colleague, Rob Scholkoff, started life as a radio astronomer, which turns out to mean he's pretty good at building microwave amplifiers. And completely changed directions, to start working in circuit QED. My other colleague, Michel Devereux, his background is in nuclear magnetic resonance. So those are all physics or astrophysics, but these days, people with backgrounds in control electronics, in software design, and systems building and verification. I mean, we need a huge range of skill sets, and you should have some depth in one of those and then pick up enough knowledge of quantum to be able to start joining the conversation. And then you'll just it'll be fun and you'll rapidly learn more.
I think that's a great answer, and there's a lot to unpack there, but I'll ask Ivan. We lost you for a minute, but I think you're back. If you would like to add anything to this question. The question, in case you didn't hear, was for people not in the field interested, is there any advice that you would give them to get into the field, essentially?
Yeah, I mean, I didn't, unfortunately, my internet's not fault tolerant here at my house. But anyway, so I didn't hear all the responses. But, I think as I heard part of the response, there's a lot going on right now at universities and other educational institutions of how you bring people who aren't necessarily physicists, because part of the issue is quantum physics or quantum mechanics and how that is, I think there's more and more effort along those lines. But I guess my general advice for, people getting into the field, generally speaking, or just getting started, is it's very hard to predict. So it's not necessarily the case that, you need to learn this or that. I think what's important is that you learn. That is to say, you study hard, you broaden your knowledge, you become well-versed in mathematics and physics, engineering, you get a broad education. You never know where it's going to take you. So, just study hard.
Always great advice. Thank you, Ivan.
Can I say one more thing, Ryan?
Yes, please, please.
So I think it's clear that all of us older folks, we came in from other backgrounds. And so all of us did not get PhDs in quantum information science. We essentially couldn't have. But one of the things that I think will be critical, even with the field as established as it is showing the flexibility and being willing to put it bluntly, look like a complete idiot, because the field is so broad that there's going to be some aspects that you don't know. And if you can bring your expertise together with somebody else who has very, very different expertise, and you may look like idiots to each other, but you'll also be able to help each other. So never get yourself in a situation where you're only willing to work on your own expertise and not get into that uncomfortable zone where you're having to interact with things you don't know so much about.
That's a great point, and it leads into a question that I wanted to ask you all. The field of quantum information is perhaps a bit unique in that there are so many different subfields, and there's so many people with different areas of expertise. Attending some talks at this conference, it was hard to understand some talks. Others, they were directly in my research area. Do you have any advice for graduate students sort of on this topic? Is it good to try to get well-versed in a lot of these different subfields, or is it better to focus on one or two and really do a deep dive into that area? Maybe starting with Steve now.
Okay, that's a hard question. What I usually say, if you're interested in research, let's say, then I think once in your life you should go deep, not too narrow, but deep in one topic. But keep looking around, because I like to say you can't be interdisciplinary without at least having a discipline. But so going deep in something lets you understand what it's like trying to work at the frontiers of knowledge, where the answer's not in the back of the book, and you have to struggle and you feel dumb and it's just hard. But you get help from people and you persist. But at the same time, once you've done that, and even while you're doing that, you should be, at least picking up a smattering of knowledge from your fellow grad students or undergrads or whatever level you're at about other areas. You should be curious. The main thing is just to be curious and want to learn something about these other areas. And you can, once you know something, you can teach it to other people, and then they can teach you what they know. And that's the way that you broaden your knowledge base. And I completely agree with what Eleanor said, that you got to be willing to get out of your comfort zone. You got to be willing to ask what seem like dumb questions. I always say to my students, there's no such thing as a dumb question, only a dumb answer. So when I'm teaching, I'm the only one at risk. But you just gotta get out there and talk to people and ask, well, where can I find a comprehensible pedagogical introduction to this thing that I'm curious about? And nowadays, with the web and with review articles coming out, I mean, this field is so new that there aren't, a lot of really, there's not years of experience in teaching this at different levels. We're still learning how to do that. So it's a little bit of a struggle sometimes to find things. But if you ask around, somebody can say, oh, Nathan Weeb has a great review on this or whatever, and you go and check it out, or you work through it as a journal club or a group and help each other learn.
I think that's great advice. Eleanor or Ivan, is there anything you would add to this response?
I guess I've always viewed the PhD process as the most important thing for you to do is to take a quite efficient path out to the edge of where research has been done and try to backfill that in. But you need to get out there. And maybe if you're super talented or unlucky and have to switch gears, you may get out to the frontier in a few areas, but it's really important to get out there. And I like to recommend that people, in addition to really focusing, have on their nightstand what I call bedtime reading. Maybe this sounds really nerdy, but find some well-written articles that are kind of fun to read that will stretch your mind in other respects. And then I can't emphasize more what Steve was saying about talking with other people. That's really just such a wonderful way to learn. And I worry that within the past year, as everybody's been more isolated, that's been harder for people to do. And I have wondered how that has impacted students. So the extent to which you can learn from each other, and the most successful people I know generally have people that they're working with closely who they can ask all sorts of questions to, and just have very, very lively interactions. So it's great you're at this event, and I hope that it can help you build those relationships going forward.
And maybe I'll just add one or two short thoughts. I mean, one of the issues in this question is about breadth versus depth. And that's a tough one. I think to some degree, I echo one of Steve's comments that it's really important. I mean, of course, it depends what you're doing. If you're, particularly we are all researchers, and this is a research conference, but to be a cutting edge researcher, depth is important. But at the same time, I do think, circling back to the first question, what's different now? Well, I think there are going to be programs that are called quantum information science, and they're going to have breadth in them, in the same way that you get a PhD in physics, you take stat mech, you take E&M, you take classical mechanics, and there will be that breadth, I think, for for the attendees here at the conference, in the kind of education that's different from the education, say, I received, with a different kind of breadth. But I do think it's important to have depth. But it's good to have maybe one other thing, depth plus one, and that to build that interdisciplinary. And that's also part of life's journey. I mean, learning new things the rest of your life is incredibly fulfilling. So, I get to learn. I never knew anything about computational complexity theory, but now I get to learn it, and that's a ton of fun. So, depth plus.
These are all great responses. Thank you for that. In the interest of time, I will move on to another question. I won't ask you when we will have fault-tolerant quantum computers, unless you know, in which case, please let us know. But this question gets thrown around a lot, and I'm interested in your thoughts. Is it useful to try and predict where the field will be, say 10 years from now or even farther? Or should we really not be thinking about this and just focus on the problems we have at hand? Let's start with Ivan for this question. Ivan, do you have thoughts about this?
I think 10 years is a long way away. At that point, it's kind of random guessing, in my opinion. But at the same time, I think it's important to understand in that kind of time frame, you know, where are hurdles? I mean, we make progress by understanding, you know, what is possible and where the roadblocks are. And roadblocks that we thought we might never get over, oh my God, we get over. And, you know, what might lie on the other side of that uh, remains to be seen. But I think it's pretty hard to predict 10 years. I think you could maybe take a guess. Are you optimistic or pessimistic? And I'm optimistic.
Eleanor or Steve, are you optimists or pessimists?
I don't know. It depends who you're comparing with, right? I mean, I'm very optimistic that fault-tolerant, scalable quantum computers will eventually be built. There are a number of people who I think completely indefensibly are saying that they will be built within the next decade for sure. And that seems way too confident. So in that sense, I might be a pessimist. But I think the most important thing about those predictions is that it really pushes people to think about what's involved and makes people have ambitious sites, helps generate excitement in the field, though one has to push back against things being too hyped. So I think really mapping out the future and even putting some vague years on it can be helpful. It's certainly fun to argue about in the over dinner or late into the evening. I think we also want to guard against about not being ambitious enough. There was criticism of the research being too academic when I started in the field, and now I don't think anyone then would have predicted that there would be so much company interest and so many startups and the like. That scares me a little bit, but that would not have happened if there weren't people predicting things in the nearer term and really pushing towards that goal.
Steve, would you have anything to add here?
Yeah, I mean, when I talk about these things or give talks about these things, I usually say that the people who developed quantum mechanics were just thinking about light and diffraction gratings and spectra and there's no way that in the fundamental nature of reality, there's no way this had anything to do with technology. But then the people that invented the transistor and the laser and the atomic clock knew it had maybe something to do with technology. But the people that soldered together the first transistor in 1947 could not imagine that today, in every second of every minute of every day, the world builds more than 20 trillion transistors. It's just, it's very hard to predict the future. You tend to overestimate what you can do in the short term and underestimate what you can do in the long term, for sure. And I agree with that. I think that's what Eleanor was saying. I'd like to echo something that Ivan said, which is, I mean, imagine that you, as an example, imagine you're a computer scientist. You'd like to get into this field. What should you work on? Should you assume that 5 or 10 years from now, we're going to have huge scale, fault tolerant quantum computers that just work? And so you should be working up here at the top of the stack on some abstract compiler that just assumes that you have a quantum computer underneath. Well, maybe, because we're going to need that work. But the hardware is pretty bad right now, and we've got to get out of the NISC era and into this fault tolerance era. And the way to do that, I think, is for computer scientists to be willing to learn something about down here at the bottom where we're struggling with what the electrons are doing. You should learn how to build compilers that know that, that qubit over there is the worst one. Don't use it except as a last resort, and all, the errors look like this, and we should be aware of the specific errors in our specific piece of hardware. I think so. We need people that are working on the today's challenges, and we need some people working on tomorrow's problems that will arise once we've solved today's problems. And you have to make an intellectual decision about which, or at least better yet, try to be working on both and have one foot in today's problems and another thinking about tomorrow's problems, because eventually we are going to succeed, and it'll go faster if you're working on both timescales.
Well, these are all great responses, and there's a lot more we could ask and dig into here. Time has flown, and we're almost at the time now. There was one more question in the Q&A, which I wanted to ask all of you about. We had a DEI panel earlier in the week where we discussed these important matters about diversity, equity, and inclusion. And I think it's exceptionally important for young researchers to start thinking about this now. So I'll leave this as a question to all of you. What are some things that we could do as a field in areas of DEI? And then do you have any tips for young researchers, especially moving forward in their career, how they can make the somewhat new field of quantum information, a very welcoming community for people of all backgrounds?
Yeah, well, of course, this is a challenge in society overall. It's a challenge specifically in STEM, which has not been the most diverse fields in general. And I think, it's a challenge that has to be faced at all levels. I think awareness of this is very helpful to ensure that, the environments that we create for our community, particularly as a professor, I could just speak for what goes on in, say, a research group, that, we have environments that are welcoming to everybody, and that not just welcoming in a kind of fluffy way, but in ways that are acknowledging of differences and different ways in which people communicate and interact, so that we can build the community more strongly than we have in the past. And I think awareness of historical problems helps us to make progress. And that's important, certainly at the University of Mexico, where we are a minority serving institution. And so, we certainly take that quite seriously.
Being aware of the past history, I think, is really great advice. Steve or Eleanor? Eleanor, would you like to add?
Sure. So I think it's very important to be able to advocate for yourself and also not burden other people. Sometimes people feel like they're the single representative of a group as opposed to an individual, and that can be way too much of a burden. And so try to push against that for yourself and try to protect others from that sort of burden. And then I'd like to quote from Ruth Bader Ginsburg's advice that I believe she received from her mom, which is that it's very useful to be a little deaf sometimes. And so speak up for yourself sometimes, but also just be a little deaf sometimes. And look after yourself, and life will be a little smoother if you just don't quite hear some things. And I think her mom was giving that to her as advice for her marriage, but I think it applies to life in general.
Yeah, that's good advice. I think the very fact that, as you mentioned, Ryan, this is a brand new field. It gives us, an opportunity to just start de novo and try to build in an inclusive atmosphere, and I think the the main thing is, or an important thing is, to make everybody comfortable being able to expose their ignorance and just ask questions. I mean, it's not, there's not just the usual kinds of diversity, but we have people with diverse training and coming from other fields where they don't know stuff which is obvious to you, and vice versa. And so that's also part of inclusion. And if people feel comfortable asking questions when they don't know the answer, or stopping a seminar speaker and saying, sorry, you're going over my head, there's probably a lot of people in the audience that are grateful if somebody says that. That kind of atmosphere then allows people to learn and to teach each other, and a lot of the other problems will, I think, be dramatically reduced if you work on that one key thing. But it is a societal problem. It's hard. It involves human beings. So we have to be kind of intentional about these things and keep working at it.
This is all great advice, and I encourage the attendees of this conference to take it to heart and start practicing it. So we're just about out of time. To close the panel, I want to ask you one more question. Is there anything that you're very excited about in the field of quantum information in the next few years, or even longer term? One thing, or maybe a few things. Any exciting experiments coming up, maybe some new technologies, open research problems, anything like this come to mind? Eleanor, I see you've unmuted.
It's hard to choose one thing. I think that there will just be an exceptional number of exciting things happening and major hardware advances. But what I like to emphasize is that as the hardware advances, this enables us to explore quantum algorithms in a way that we've been really only been able to do with our hands behind our back. So a lot of classical algorithms, the way one explores them is that one has some hunches and then one tries them out and see how they perform on the problems you're really interested in. And because there's in general, an exponential overhead to simulating a quantum algorithm, and the hardware is in very early stages, we've only been able to touch on that. And so I think one of the really exciting things in the coming years, we'll be able to do algorithm exploration in this other way, and that will see a broadening of quantum algorithms and clear indications of where there may be some advantages beyond what we've seen so far. And I'm a mathematician by training. I love it when we can prove something about these algorithms, but even just for classical algorithms, that's not realistic in most cases. And so I'm really excited about seeing the field open up for that.
I think there's a quote by Don Knuth, you have to see an algorithm to believe it. So I agree, this is a very exciting. Ivan or Steve, anything exciting to you?
Yeah, I think there are a couple of things to say. One is, this is a little bit something close to my heart. I'm excited to see what the mammal in the species of quantum hardware of neutral atoms. Ion traps are the cousin of neutral atoms, but neutral atoms were neglected for 20 years because BEC was more interesting. to the experimentalists. But now they've got, I think we're going to see 1,000 qubit quantum processor with neutral atoms within the next few years. So look out for neutral atoms. It's on the rise. The other thing I'm very excited about is for the future, and I think it's something, you know, going back to what got me into the field in the first place, which is we still don't understand quantum mechanics. And I think we will. I think we'll have a better understanding of quantum mechanics. And I think we should still be thinking about that. We shouldn't just shut up and calculate, because I think it's important. Because the framework of thought is what enabled quantum information processing in the first place. If we can't think about quantum mechanics properly, we can't use it. And so it's still important to do that. And I'm excited that people will still think about that.
Yeah, those are, you both made great points. You know, I always remind people, you know, quantum information processing didn't come from, you know, extending quantum mechanics or, you know, improving it. It's the same old theory that we had, you know, you could have done this in 1930. It was a point of view. It was asking questions about what is the information content of a quantum state. And so that's a very good point. With respect to, I mean, to echo what Eleanor said, I mean, I'd like to remind people that, you know, when von Neumann built early computer in Princeton, they were programming it by taking patch cords, you know, wires like an old-fashioned telephone switchboards, and plugging them together, and then booting the system by switches that individually set a few bits. I mean, it was a nightmare. And that was so painful to do this, they started thinking about there must be a better way. And eventually they came to the idea of the von Neumann architecture, that you should treat the instructions the same way as the data, so that you could overwrite the instructions and crash your computer. But anyway, but that, you know, that breakthrough, you know, came out of the pain of hacking around with the hardware. And I think that's exactly what Eleanor is saying, that now that you have access to online quantum computers, young people are going to start playing with them and build up some intuition about how quantum mechanics work, to speak to Ivan's point, and build up some experience with algorithms, to speak to Eleanor's point. And they're just going to figure out how to get these things to actually work. My own personal interest, the thing I'm most excited about, is quantum error correction and fault tolerance. And the way that I and my colleagues are most excited about trying to do that is using quantum information stored not in traditional qubits, but in continuous variable systems, in harmonic oscillators. For us, microwave photons stored in resonators, or mechanical oscillations. And you know, we're in the very, very earliest stages of error correction. There's been a handful of experiments in which carrying out the error correction protocol made things not worse. And that's you know, we've got to do a lot better than that. Carrying out the error correction has to make things thousands of times better. And, you know, we've made it 30% better. So it's just, and we have to solve this problem. We can make the qubits better with better materials and better designs. We have to do that. But we have to solve the fault tolerance problem, which roughly, it's hard to define fault tolerance a little bit, but roughly speaking, it means you can do quantum error correction on faulty hardware using faulty hardware to do the correction. That it works even if the controller makes a mistake. The fact that that's even possible in theory is stunning. And again, von Neumann was one of the early people that thought about this, but getting it done in practice is still pretty hard. So that's
And
what
von
I'm
Neumann,
excited about.
and von Neumann initially thought it wasn't possible classically, and that was one of his biggest mistakes, though he realized it himself and then
Right.
figured out what to do. But it's fascinating that he thought it was impossible for a bit.
Yeah, yeah. And he was thinking about, human brains. I mean, they're just this mush. How could they possibly do anything reliable? And he started thinking about neural networks and things. So he was a fairly smart dude, it turns out.
I think this is a good place to end the panel. We have algorithms in practice, neutral atoms with thousands of qubits, maybe even understanding quantum mechanics finally, and then quantum error correction in practice, not only in theory. I wish we could have a round of applause to thank you all, but thank you, Steve, Eleanor, and Ivan. I think this was a great discussion. And please, everyone in the chat, thank them as well. It's been great to pick your brain for the last 50 minutes or so, and we really appreciate you taking time out of your very busy schedules for this. So thank you again.